So we want to kind of pick up where we left off, and maybe where we left off, we were, I'm writing things and it's disappearing. Why is that? Why is that? It's like I'm writing with disappearing ink here.
You just have to cut it down really quick.
What's going on? Delta G of reaction. We were kind of at this point, I think. We had gotten that far, where the delta G of reaction equals the delta G, this is reaction, at standard conditions. I think this comes up a little bit further on in the slides, but the question comes, what's the difference between this and this? All right, and that's going to be important as we move along here. This is a constant. This is for a particular reaction, written in a particular way, the number of moles of whatever involved in that reaction, you're going to get a delta G naught of reaction, a standard change in free energy for that reaction. You're looking at a reaction that's at 298 Kelvin and 1 atmosphere pressure. So the conditions of this reaction are specified and leading to a constant number. It's characteristic of the reaction as you wrote it, however the reaction is written. This delta G is not a constant. It can have any value depending upon what conditions the reaction is being run under. Pressure changes, temperature changes, that number changes. So this number, you're calculating a particular number here that is specific to the reaction written under the conditions in which that reaction was run. This is a constant number. So that's going to be a critical piece of information in a few minutes as we segue from this general equation that has this relationship that the delta G of the reaction is the standard change in free energy plus RT times ln, this reaction quotient. We're going to move to a point where we start looking at a specific Q. All right, they all reappeared. Wasn't awake yet. Ben wasn't awake yet. All right, we kind of ended here. Just look at a couple slides. I had you calculate this. All right, and you all raced one another and got to this number right here. Where is that number? Yeah. Q equals 0.179. So that is being plowed into that equation I just showed you. Delta G of the reaction is equal to delta G naught plus RT ln Q. All right, so this is just a general situation. We're going to start drilling down to something more specific. And we get a delta G here, we get a Q. Q is showing the relationship between these partial pressures of the hydrogen, the oxygen, and the water. Let's see. Here's another one. We got H2O gas at 25 degrees C. This is right out of the book. That's not the standard state of H2O, but for this for this particular example, I'm not sure if these are really logical values, okay? It's not really logical that we'd be looking at water. I mean, water will have a vapor pressure, but I don't know that that's what they're looking at here. But at any rate, punching that all in and just using that as an example, we get this Q for those partial pressures. Punch it into this equation. We're converting the joules here to kilojoules and getting a delta G of reaction of negative 461 kilojoules. Is that reaction at equilibrium? What's the condition for the reaction to be at equilibrium?
Well, the reaction in the forward direction is the same direction in the backward direction, like the speed of it.
Well, that's one condition.
Oh, delta G 0?
Delta G is equal to 0. So this is not at equilibrium.
Delta G not, or delta?
This
Yeah,
delta G.
Okay.
The delta G of the reaction would equal 0. So when delta G equals 0, yeah, good clarification. Delta G of the reaction equals 0, then it's at equilibrium. Oh, okay. That's okay. We'll leave this slide here, and I'll just leave it there for you if you care to do a problem. But basically, this would be to just take that equation and do an example. So, in the interest of time, I'll leave this for you to do. But you would be addressing this with this equation.
So, if we're looking for when delta G would be equal to 0 at equilibrium, could we solve for that equilibrium constant by just using delta G? Like, look up the values in the book and then set variables equal to like how much they should be, and then solve.
Solve for what?
Solve for K.
Q? Yeah, Q. Q and K.
Well, yeah, K. Sorry, Q. Yeah.
Q and K. And that's right where we're going. Yes, yes. But this, just to toss this example in here, so what you would need to do here is set up a relationship for Q. You've got the partial pressure of nitrogen, the partial pressure of hydrogen, the partial pressure of ammonia. Let's just think it through without doing the calculation. I'll leave it to you to do it later. But remember, Q is this thing, where this is your products. It's the product of the partial pressures over standard pressure of the various different products. And this is going to be this. Now this is J, this is reactants.
Is the standard pressure always going to be 1?
Yeah, one bar, or yeah, 1 atmosphere. 1 atmosphere. So let's see what this would look like. If we have products, what we have hydrogen, so it's going to be the partial pressure of hydrogen divided by 1, and it's going to be cubed, right? Times the partial pressure of nitrogen, P naught, and that is going to be just the power 1 divided by the partial pressure of ammonia. And in some of these examples, they have AM there instead of NH3. I think they're talking about the Americas. I don't know what they're talking about. So, and that's going to be squared. Because remember, it's to the absolute value of the of the coefficients. I keep saying we're not going to calculate this. Somebody have it already? Don't worry about it. You don't have to worry about it.
Times 10 to the negative.
You got a number?
Yeah, 8.17 times 10 to the negative fifth.
Times 10 to the negative fifth?
Yeah.
Okay.
Does that sound right? Did you guys get that?
Yeah, that sounds right. You're going to have 12.9 in the denominator squared.
Yeah, that's really big.
Yeah, that sounds right. And so then, basically all you're doing then is taking that Q and plugging it into this equation. Our temperature is going to be 298, 8.314. Yeah, this is unitless.
Yeah, it's gonna ask.
Yeah, I thought the same.
So
Okay. So it's unitless? It's not
Yeah.
like ATM squared or
no.
anything weird? Okay.
Yeah, I guess you've got ATMs here divided by ATMs. They're crossing out, and then you're cubing that ratio.
Oh, you're cubing nothing, yeah.
Yeah, you're cubing that ratio. The units have already crossed. Okay, so that is just to take that fundamental equation, or a good equation. We're going to get to an even more fundamental one right now. But that is our base equation. All right, so now let's segue on from there. Yeah, and I've already made the point, the difference between the delta G of reaction and the standard delta G of reaction. All right, so for chemical equilibrium, the delta G of reaction is going to equal 0. So in this,
Not just a superpressure. There's just nothing given in the problem.
are you back here? Are you finishing this?
Yeah.
Yeah, it's just one.
Peanut is one.
Yeah.
It's always one.
Pressure at standard conditions.
Oh, pressure.
Pressure at standard conditions. So whenever you're seeing this knot, just think standard conditions. We're going to even see C knot come up, and that's going to be standard concentration. And standard concentration is 1 molar. Standard pressure is 1 atmosphere. Standard temperature is 298. Sorry about that. Got some people doing some work at my house. That was the other call I took the other day in order to get the commitment for them to come and do that. All right. So, yeah, standard free energy is free energy at standard conditions, 298 Kelvin and 1 atmosphere pressure. All right, so we got this reaction, or this equation. If we set delta G equal to 0, so we have the delta G naught of reaction plus RT log of Q equals 0. This is at equilibrium. And so then delta G naught of reaction equals negative RT times the log of Q. Okay, this reaction quotient now is going to take on more significant meaning right now. At equilibrium, as I was saying, this number is a constant. All right, this is a constant. This is going to be a certain number, whatever temperature we happen to be running at. And so this is going to be a constant associated with this. Q is a constant. At equilibrium, Q is K, and that's our equilibrium constant. So we've been talking about Q as a general number up to this point in time, but when we start really focusing on equilibrium conditions, we're talking about a specific Q, which is this constant number, an equilibrium constant, for the reaction the way it is written. I mean, so you have to keep in mind the particular reaction you're talking about. All right, so let's see where we go with that equation. I left a whole lot of space for a whole lot more equations, but that's basically it. And I plopped it back down there because that is the number in the text, equation 510. And you can see the author loves to write the reaction first before the G. He may be right. I haven't looked at too many other textbooks, but I'm used to writing it after the G. But let's look at an example that he has there briefly, and then I want to go into a little bit more detail with the next example that he has. This is kind of an eye chart here. For the gas phase reaction, so we're talking a lot gases, well, right now. For the gas phase reaction, ethyl acetate, water, going to acetic acid and ethanol, the equilibrium constant is 4 at 120 degrees centigrade. If you start with 1 bar of both ethyl acetate and water in a 10-liter container, what is the extent of the reaction at equilibrium? What is the delta G of the reaction at equilibrium? And what is the delta G naught at equilibrium? Explain. So here's the initial conditions. None of this. 1 bar of ethyl acetate, 1 bar of water. Now we're at 120 degrees centigrade, so it makes sense that we could be in the gas phase with all these things. I don't know what the boiling point of ethyl acetate is offhand. It's probably lower than water. It's not very polar.
Yeah, it's pretty low.
Yeah, it's
Yeah, pretty. It's not polar, very polar.
Butyls like 120. So.
All right, so at equilibrium, something's going to happen. It's obviously going to shift towards products. You've got only reactants, no products. It's going to shift towards products. So let's say you get X bars of each one of these. You're going to have 1 minus X of each one of these. So K, so at equilibrium, we're going to have delta G of the reaction is what? Question B. Well, we'll see. It says, what is the extent of the reaction? So we want to see what this number is going to be, and we could see how this changes, and we could calculate extent. I'm not sure if I put the rest of this example in here. But you're going to end, so you get down here, you get down to this point where you have this equation, which I want you to solve right now. Okay, solve for X. This is the first time we're bumping into, I'm sure it's not the first time you've bumped into quadratic equations, but I think it's the first time we're bumping into one in a problem in here. Okay with that far? So this is going to kind of come around to this.
X equals 2/3 of 2.
Okay. All right, so you have to rationalize that quadratic. And what'd you get, Liz? Here, wait, before you get the answer, you got a 3x here. Is that what you got?
I did the lazy man's way and I typed it into my calculator.
Is that right? Okay. I want you to take the stroll down quadratic equations and crunch it out.
Math.
All right?
Well, can we use like the program or calculator?
Okay, you could.
I have a program.
And Liz has got the right answer, but here's what it would factor out to these two things. And so this could be equal to 0, or that could be equal to 0, and that ends up with 2/3 or 2.
So how do we decide which one's right?
Okay, let's figure out, how do we decide which one's right? What is x? X is the amount. Well, let me just make this a little bit smaller so we can see it all. What is x going to be? X is going to be the amount, the number of moles of these it's produced, and it's going to be the number of moles you lose of these other two reactants, right?
Yeah.
So is that a logical number?
Not for this one, though.
No, not for this one. So we can discredit that one because you can't lose 2 moles of either of those reactants. But you can lose 0.667 moles.
What if we end up with 2 numbers that are reasonable?
Well, let's hope that your structure doesn't give you a problem.
Okay.
All right?
You guessed right.
Or you claim that he didn't tell you what to do in a case like that.
Sounds good.
That might work. I mean, that excuse might work.
Okay.
Okay, so x equals 0.667. All right. I don't think I have the rest of this example, do I? No, I don't. This is example 5.5, and they carried on from there. I just wanted to crunch down through there to see how we would solve and decide what to go with. So this one I do want us to crunch out the whole thing. So get ready for this one, and don't look at your book because this is in the book. This is example 5.6. I'm gonna lead us through, or at least get us started down a path that is a little different than the way the author approached it. They both give the right answer. They both get the same point in answering it. I just think the author went through a few steps that I would have just gone at it a little bit differently. So let's look at this problem and set it up. Molecular iodine dissociates into atomic iodine at relatively moderate temperatures. So they're calling 1,000 Kelvin relatively moderate. Okay? You know, a day like today, the snow would be gone really fast. So would the trees and everything else. So, relatively moderate. All right. 1,000 degrees Kelvin for a 1 liter system has 6.0 times 10 to the minus 3 moles of iodine present initially. The final equilibrium pressure, total pressure, is 0.750 atmospheres. Determine the equilibrium amounts of iodine and of diatomic iodine and monatomic iodine, calculate the equilibrium constant and determine the extent of the reaction if the relevant equilibrium is this. One iodine dissociates into two, one molecule dissociates into two atoms. Assume ideal behavior. Okay, so we got iodine, the molecule, and the atom. Initially, what do we have? We have 6.00 times 10 to the minus third moles, and we have 0 moles. At equilibrium, let's say we get X moles of iodine atoms. No, let's not say that. Let's say that X moles of iodine dissociates. And so we will get, Taja, how much iodine atoms will we get? Well, if 1 mole of this dissociates...
Sorry, my bad. 2x.
Okay, you just got to go by the coefficient. We're going to get 2x moles of that. So, so actually, we got a couple equations for the total moles. Total moles at the end are going to be this. Right? And what is another equation we can write for the total moles at the end of the reaction? What is another equation we can write? Assume ideal behavior.
Pressure, temperature, and volume.
Yeah, we're given temperature, we've got volume, we've got pressure.
The ideal gas equation.
Yeah, so N total is going to be PV over RT. Okay, why don't you work on this a little bit? Solve for X.
Couldn't we just use pigment for the whole thing?
Well, that is what the author does. He does use Pivnert for the whole thing. All right, go through it. Go through it this way, and then you decide which way you'd rather do it. What you're going to have to do here is calculate the moles of each of them, and then mole fractions. You're going to have to use the mole fractions to figure out the partial pressures. Let's keep in step with everybody so that you don't run down this whole track with the wrong answer. What N total do you get from Pivnert?
0.0914.
Yeah.
That's what I got. Good for temperature.
Divided by 1,000. And then 750 times 1 plus 1,000. Did you say 750?
That's a lot of pressure.
Yeah, good. So x equals what?
00314.
Good catch.
Was about to be really loud.
Thank you.
Upstairs and downstairs. It's a nice thermos. So at equilibrium, finally, we have what kind of values? For iodine. Yeah, okay. And atoms?
It says determine the extent.
Oh, we have to determine the extent.
You have to figure out what that equation is.
Yeah, where's that equation?
Did you give us that equation by any chance?
Yep. It's the final moles minus the initial moles divided by the coefficient.
Okay, final moles.
Final moles divided. So
Divided by coefficient.
that's where that new I came in. And remember, the coefficient is negative for a reactant and positive for a product. And extent can be positive or negative. We were debating that the other day.
It's coefficient positive for a reactant and negative.
It's negative for a reactant, positive for a product.
For this one, depends on what you solve for. If you're solving with the I2, it's just going to be -1.
And remember, extent, you could calculate extent on any species in the reaction. You should get the same extent. You do not get, you should get the same extent of reaction, no matter what species you decide to pick to do the calculation.
How would you go about this equation?
K doesn't always equal x squared over 1 minus x, right? Or does it?
K what?
Does K always equal x squared over 1 minus x? Equilibrium constant. It's gonna.
No.
It's the products over the reactants, right?
So
And
Yeah, it's
this-
products over the
This is 2x squared over 1 minus x squared.
Not 1, but 6 times 7 to the third minus x. That's not squared.
1 minus x in the previous problem was because we started with 1 bar. We started with 1 bar, so it was,
Well, because here we're starting with 1 mole, and then we're losing
no, we're starting with 6.0 times 10 to the minus third moles.
that, yeah. Okay.
Yeah.
So we have that, and then I guess I'm just confused how we just calculate K. Like,
Okay, well, you got extent?
oh yeah, 3.14 times something.
Okay. So, yeah, and I don't know. I thought this was a brilliant way of doing it. It might have been around the barn. But if you took, okay, what is K going to be? Let's look at what K is going to be, and then let's look ahead how to do that. K is going to be, we've got this thing here of the products, the sum of the partial pressure over this of the reactants, the partial pressure P naught, P P over P naught for reactance. And it's going to be to that coefficient. So the products are, it's going to be the pressure of the iodine divided by standard pressure squared divided by the pressure of the diatomic iodine over, no, wait a minute here.
Yeah. I don't know if this is allowed, but can't you just plug in the mole numbers
That's what I
and
did.
square them, or and then like treat them like concentrations?
Well, you,
Or is that like gonna get you the wrong answer?
Well, I'm hesitating for a minute because it might work here because we have gases. It might not work.
well, and we only have one reactant product.
Yeah.
We don't really have a, oh, I guess we do have a concentration. We have a volume. Well, let's see.
Volume.
Let's see. So what I need to know, is what is the partial pressure of the iodine, and the partial pressure of the iodine would be equal to the mole fraction of iodine times the total pressure. So the mole fraction of the iodine is 6 point, right here, 6.28 times 10 to the minus third moles of iodine atoms over that number of total moles times 0.750 atmospheres. That's your partial pressure of iodine. And the partial pressure of the molecular iodine is 2.86 times 10 to the minus third moles of iodine divided by the total moles times 0.750 atmospheres. That's the total pressure. Do you get something like this? Is that all right?
I haven't calculated it. I will do it.
You with me, Liz?
I'm with you.
And you getting these numbers?
Why can't you just do it with the
Pivner?
molar amount?
Well,
We know
look,
how many moles the reactants and the products use, so shouldn't we be able to plug that in to the initial equation and do 2x squared over 6 times 10 to the negative third minus x?
Okay.
That equals k?
okay, I'll tell you what. Let's see.
Okay.
Okay, let's just punch these numbers up into here.
Okay.
So we have, this is our iodine. So wait a minute. So that number's going to go in there?
I think your answers are flipped. Because for PI, I got 0.515, and for PI2, I got 0.325.
Okay, okay. Okay, I do have them flipped. Sorry.
No, that's fine.
.235. Okay, so we're going to have, and if P naught is 1, we basically have 0.515 squared over 0.235 to the first power, right? And that's going to be K. Is that right?
So So our P naught is still 1 ATM, and it's not just the original or the pressure at equilibrium.
Yeah, it's still one atmosphere.
Okay.
This is the total pressure at equilibrium, and we're just using that total pressure in these partial pressures. So the pressure of iodine is the partial, the mole fraction times the total pressure. Okay? So we're dragging along all these equations that we learned before. That the pressure of each individual component is its mole fraction times the total pressure. So I'm getting K equals 1.13.
Yep. What's unitless?
Yeah. Extent. Okay, well let's just pause there for a second. And Liz and Dominic, I think, both said, why can't we just use the moles? So let's try that. So that's what we have there. I'm trying to see how I can position this so we can see things. Here's our moles of iodine, is that right? And that's our moles, molecular iodine, atomic iodine. So we would have something like this, 6.28 times 10 to the minus third. And Liz, you would want to square that?
Yeah. You should also multiply it by 2, right?
Well, we already multiplied it, and the x is 3.14 times 10 to the minus third. So we've already multiplied it by 2 to get it to that number.
Okay.
Let's, I don't know, what do you get here? Let's see what we get. Get
Is extent unitless?
no. Extent has the unit of moles because you just have moles divided by a coefficient.
Yeah, I didn't know if you're, because the coefficient you technically have units of moles, so I didn't know if you're counting that or not.
Yeah. So no, the extent has the unit of moles. This is what I get that way, Liz. Yeah, and is it
I'm just trying to figure out why
it doesn't
why
work?
does it not work?
Yeah, this isn't a molarity. I mean, this is moles of gas per liter of volume. This isn't a molarity concentration. This is just a vapors in a 1 liter volume. So I think we're trying to take the solution approach to it up into a gas phase, and that's not working. So it's a good thought. I mean, coming from equilibrium constants, and that's where we want to go next. Is we want to, everything we've been talking about so far has got to do with gases. We want to start moving towards solids and liquids and dissolved solutes. Yeah.
You said that there's a way, or that the book did this problem just with Pivnert without using the whole chart of finding equilibrium amounts.
Right.
How did the book go about doing that?
Okay.
Using the
What example is this? 5.6. Yeah. You can see, that is the longest example I think he's had so far, 5.6. That whole page and there finishes over here. Extent, he got 3.00314 moles. Okay, the partial pressures he's got down here is 0.515, 0.235. Now, the way we went about it, we got to these numbers to then calculate K.
It looks like you still use K.
He used Pivnert. He used Pivnert all up in here. He has K. Let me try to put it up in front of us here. That's a good question, Grant. He has that K is this relationship.
So, yeah, P equals RT. That makes sense.
So he has this, and what does he do from there? He says that what is PI? PI is 2x times, he uses Pivnert right here, 0.08205 times 1,000 degrees Kelvin divided by 1 liter. And of course, that's all going to be divided by 1 atmosphere. And, well, look what he did here. I mean, guys, I'm only coming over here, guys. I'm not trying to, but there's 3 here. This political party over here has more members. But no, look at this a second. Now just tell me if this isn't a mistake. K equals that, okay? Now he drops down to here and he moves the square sign into the denominator.
That's no bueno.
I don't think they actually did the calculation that way because they do get the right answers down here. But I think they misplaced that. What do you think? Does that look wrong?
Wait. I2, because it goes to I. And so
See,
2x has to be associated with I2.
Yeah.
So it's not going to make me move it up. They actually put that down there.
Okay, that look right?
Yeah, I think they are.
Right?
I know.
They just did something wrong. They just did something
Yeah,
wrong.
that's right.
Yeah. Yeah. Here, do you have it? See here?
Yeah.
And so here's where they're using Pivnert. Right out of the get-go, they're using Pivnert. I decided to go down through mole fractions. I don't know which one you would think is more. I think it's less complicated than all of that.
I mean, I think
math.
you made it a little bit more complicated than it needs to be.
Yeah, I feel like
You just solve for initial pressure, right?
Oh,
You have
Right.
the initial moles, and you have everything else that's initial, right?
No, I'm solving for the final pressure. We're solving for the partial
No,
pressure.
you're given the equilibrium final pressure,
Yeah,
0.750,
yeah.
and you can solve for initial pressure, which is 0.5 or 0.49, and so that ratio is equal to the mole ratio, like the final mole amount.
Okay, you're getting an initial pressure from those
Yeah,
from the iodine.
From 1,000, the initial mole.
Initial
by
pressure.
and liters, and you get 0.49.
So how does the initial pressure help you? How does that help you?
An increase in moles is equal to the ratio of an increase in
Pressure.
pressure.
Okay.
And so you can set those equal to each other. I think that's probably how.
Okay. Okay.
Yeah, it's basically the same thing, just written differently.
Okay. Well, take a look at it. Take a look at what we just did. We probably want to ignore this. Okay.
Wait, that's wrong.
That's the right one.
Oh, shoot.
What?
Oh.
I was like, I thought we did all the work for that.
Let's see if I can just erase those lines. Ah, look at this. Oh, beautiful. We want to ignore
On a
that.
whiteboard.
No. That's this disappearing ink. I love it. Okay, we want to ignore that one. We want to stick with that one. And then you could actually even, I don't know if it asks you to do this, you could calculate, I guess, a delta G of reaction, because now you could do something with that K. You could calculate the delta G. All right, good enough for that. Let's move on a little bit here, and then we'll get an idea what we're going to do Wednesday. Hopefully we'll finish the chapter. So that's going to bring us to here. Yeah, I got a couple more pages I want to try to do. Okay, how are solids, liquids, and dissolved solutes represented? So far here we've been kind of doing everything based on gases. We've been concentrating on gases, partial pressures of gases. We've been using that to define Q and getting to a K, but mostly dealing with gases. So how do we start broadening this whole approach to things to solids, liquids, and dissolved solutes? How do we get those represented in an equilibrium constant? So that involves chemical activity, A, this term A. And it's defined in terms of, so it's defined in terms of standard chemical potential. The standard chemical potential, so that's going to have a naught on it. Mu sub I naught, and chemical potentials under standard pressures. It's mu sub I. Right, and we get this equation, I think, mu sub I naught equals RT times the log of the activity. So now we're going to talk about activities more than partial pressures. Activities. And this is a for gases, the activity is the fugacity over standard pressure. So gases have an activity. Solids, liquids, and dissolved solutes are going to have an activity. It's just a broader concept to work with.
Is there supposed to be two equals in there?
No. Plus. Thank you.
Genius over here.
Have you all... I can see why engineers love pencils. I mean, I used to work with pens all the time. And then I said, I realized I was going to teach PChem. First thing I did was run out and buy. I said, okay, what size lead do engineers like?
5.
5.
A lot of people use 7.
7.
But like I prefer 5.
This is 9. I think I'm going to switch over to 7.
3 is a quality one too if you want to fit most stuff on it.
Oh, that's too fine.
3 is 5.
3 just seems too fine. I mean,
5 is really small.
if you want your instructor to see it, at least a 0.7.
Oh no, you can see 5.
Okay. All right. No, thank you. That's a plus, not an equal. So that now we're going to get here. We're not going to get bogged down in all this derivation. I just want this general equation now is going to be the AI's to the, again, to the new I's, the coefficients of the products, and then we're going to have one here for the reactants, is the AJ's of the reactants, and the absolute value of the coefficients of those reactants. So this is the product series for however many reactants there are, the product series for how many products there are, and that's Q. And so that's becoming a broader term that can bring in solids, liquids, and solutes into the discussion now. Okay, now the author refers to an equation in chapter 4. I didn't get the equation number. In chapter 4, not methane. In chapter 4, there was this equation: the partial of the chemical potential with respect to pressure at constant temperature is equal to the molar volume of that species. And so then we can through a couple of equations get this down to the log of the activity, natural log of the activity, is equal to the molar volume divided by RT times pressure minus 1. Okay, and I repeat that equation right here. Okay, so that's equation 5.14. The natural log of the activity is the molar volume of the species divided by RT times P minus 1. Okay, don't worry about the derivation of it. Worry about the use of this one. Just so how would we use it? And this will probably stop. We won't stop right here. We're going to do one more quick calculation. Take a look at example 5.7 from the book. Determine the activity of liquid water. Okay, now we're talking about a liquid. It's at 25 degrees C, 100 bar pressure. The molar volume of water at this temperature is 18.07 cubic centimeters. Using equation 514, so we had this ln of AI equals the molar volume divided by RT times P minus 1. So that's equation 5.14. Molar volume, RT, we're just converting the molar volume here into liters. That's all we're doing right here. What's the pressure? 100 bars minus 1, or standard pressure. And we get the natural log of AI equals 0.0722. AI equals 1.07. The point here is that is approximately 1. But what I want you to do, just before we leave, real quickly, do this calculation, but change that to 10 bars. Now remember, a bar is about an atmosphere. So that's 100 atmospheres. That's very high pressure. So let's bring it down to something that's still pretty high pressure, 10 atmospheres, and redo that calculation and solve for AI. And this will be a good place to, with the closing statement. So what is AI now?
I got 1.00656.
Okay, so that would round off to maybe 1.01, 1.006. So AI at 10 bars, AI equals 1.01. Okay, the point here is this. This is the point. And this is right out of the text. Therefore, in most cases, the activities of condensed phases can be approximated as 1 and they make no numerical contribution to the value of the reaction quotient or equilibrium constant. Remember when you looked at Kw? Kw is the molar concentration of the hydroxide times the molar concentration of the hydrogen, and there's no water in the water wasn't in the denominator.
Yeah.
Okay? Why? It washes out of that thing. It's basically 1. And you can think about this. Pressure on a liquid doesn't have a lot of effect on a liquid. Liquids aren't compressible. So the liquid is falling out of these constants. And we'll go on now and look at solutes. And we will do a couple of the Chapter 5 problems in class on Wednesday. Probably number 3, where it talks about a KP and a KC. If you start tripping over that, we'll do that problem in class.
Thank you.
All right. See you Wednesday. Bring these back in, because bring this set back in, because we're going to pick up on this set. These set of slides.